Hey everyone, my name is Alex Tong Lin, and I'd like to thank the organizers of this conference and also the audience for having such a nice conference. Today I'll be talking about decentralized multi-agents by imitation of a centralized controller. So first I'll talk about what multi-agent reinforced learning is, and then I'll talk about some algorithms that can be categorized as a bottom-up approach, and then I'll be talking about our work SESMA, which can be seen as a more top-down approach, and then I'll talk about numerical experiments. So multi-agent reinforced learning. So I'm sure all of you have heard what reinforced learning is. Basically, it's the study of determining how an agent should take actions in an environment in order to maximize a cumulative reward. So you have an agent here where it will see a state and a reward, and then it'll take an action. And then this action will have an effect on the environment, and then the interpreter will then issue a new state and a new reward. And the goal of reinforced learning is to find the best policy that will output actions that maximize the cumulative reward. Multi-agent reinforced learning is the study of how multiple agents should act and take actions in the environment and interact with each other in order to maximize their own cumulative reward. Note that a key feature is that the agents must act in a decentralized manner, so they can only observe their own local states when they act. And so for example here, each agent can only output its own action, and when it receives a state, it can only observe its own local state, like S sub 1 here, and then S sub 2 for agent 2, and etc. I'd also like to note that from the perspective of each individual agent, the environment, which includes the other agents, will be non-Markovian. Okay, so why is that? Well, okay, we can contrast it with perhaps a Markovian problem. Okay, so pretend you're playing golf, you're a single agent playing golf, and let's disregard the weather. Then, it's pretty clear, wherever the ball is, it's pretty clear what the optimal action you should take is. But if you're playing something like soccer, where now you have an opponent who is learning and updating, when I'm playing soccer and I try to score a goal against a goalie, I can do maybe a little trick, and that can maybe score the goal. But the next time I try to do the trick, the goalie will have seen it and will have learned. So now I can't do the trick again to score a goal. I have to do something else. I have to be a little more clever. So the environment in this case is non-Markovian. So yeah, in multi-agent reinforced learning, the environment is non-Markovian inherently. Now, cooperative multi-agent reinforced learning is a subset of multi-agent reinforced learning where now there is a single shared reward among all agents. And this is sort of like now the agents have to work as a team. So individual rewards don't matter. It's more about the performance of the whole team. So of course the rewards will now be shared. If we look at the value function for reinforced learning and the value function of cooperative multi-agent reinforced learning, they're similar, but there are a few key differences. So in RL, the idea is you want to find the best policy that maximizes the value function, which is going to be the expected cumulative reward. In cooperative multi-agent reinforced learning, now we want to find the best joint policy that maximizes the value function, where the value function will be the expected cumulative shared reward. And if you notice, I've changed the S's into O's because in multi-agent reinforced learning, it's more common to talk about the observation rather than the state, because I guess a state sort of denotes the state of the whole environment. But of course, from the perspective of each agent, it only receives an observation of the environment, not the whole state. And also note that the observations, the O's here and the A's are bolded to denote that they're joint actions and joint states. The bottom-up approach. So now I'll be talking about a couple algorithms that can be categorized as the bottom-up approach to multi-agent reinforced learning. Perhaps the most straightforward way to extend reinforced learning to multi-agent reinforced learning is to just basically have each agent learn independently. So if we have M agents, then you can think of independent Q learning as just deploying M Q learning algorithms for each agent and then just updating each parameter sequentially. And so each agent just sort of pretends it's in its own little world where all the other agents are just merely part of the environment. So there's no cooperation, no talking to each other, nothing with shared parameters, nothing. It's just M Q learning algorithms running in parallel. Of course, this has issues with convergence due to the non-Markovian nature of the environment. So one way to solve the multi-agent reinforced learning problem, and also this non-Markovian problem, is a multi-agent deep deterministic policy gradient. So this basically takes the actor-critic model and expands it to the multi-agent setting. And note that the framework it uses is centralized learning but decentralized execution. So this diagram basically explains it all. So during the training phase, the critic of the actor-critic will be able to take in the joint states and the joint actions. And then it'll be able to output and give advice, sort of, to the actor pi. And the pi will output its own local action and take in only its local observation. But then the critic, of course, will take in the joint observation, joint actions. So you can think of the critics here as sort of like a coach that's each coaching its own actor. And this is, of course, during the training phase. But during the execution phase, we get rid of the critic and we just let the actors act. And of course, they will only receive its joint observation and output local actions. So at the end of the day, we're able to solve the multi-agent reinforcement learning problem by having these actors that act in a decentralized manner. So these methods can be described as a more bottom-up approach, where they try to build the solution to the multi-agent reinforcement learning problem while they build up a solution while simultaneously solving the environment. So now I'll talk about our work, SESMA, and how it can be seen more as a top-down approach. So SESMA is centralized expert supervised multi-agents. And basically the idea is you take a centralized expert that will take in the joint observations and output joint actions and solve the environment that way, where you can sort of view it as a single agent reinforcement learning problem. And then after the centralized expert sufficiently learns the environment, then we can use imitation learning to decentralize the centralized expert in order to attain decentralized multi-agents. Note that this also falls under the framework of centralized learning but decentralized execution. So we can describe SESMA in two phases. In the first phase, the centralized expert basically learns the whole environment in a single agent fashion. So it just takes in the joint observations and the reward, and then outputs a joint action. And you do this enough, and hopefully you'll solve the environment. And you can solve the environment using any single agent reinforced learning algorithm. In phase 2, that's when we try to decentralize the centralized expert in order to attain decentralized multi-agents. So here we have the agents that are outputting its actions and going through the environment, and then the environment will issue the next observation, which will be given to the agents, but also it will be given to the centralized expert here. And the centralized expert will then output an expert action. And then we'll be saving this observation and expert action into a data set, almost like an experience replay buffer. And so we basically let the agents run through the environment, but saving the observations that it sees. And perhaps every k runs of the environment, we do supervised learning / imitation learning on the agents. So, basically the input to agent 1 will be O1, and then we want it to, and the label will be the expert action A*1. And so the agent will just merely try to mimic the expert's advice, the expert action. And hopefully, if all goes well, you'll get decentralized agents that work just as well as the centralized expert. Or close. Now I'll talk about the numerical experiments. For this first numerical experiment, we have this cooperative navigation environment, where the goal of the agents, shown in purple, is to cover the landmarks, shown in gray. Now, to incentivize the agents to cover the landmarks, we make the reward calculation like so. For each landmark, we find the minimum distance agent, and then we take that distance. And we do that for each landmark and take the sum and then put a negative in front of it in order to penalize it. And we also penalize collisions. And so the reward is basically going to be negative of these distances minus the number of collisions. Also note that these agents are going to be non-homogeneous, and the smaller agents are smaller, so maybe they'll collide less, but they're also faster. And the bigger agents are bigger, they'll collide maybe more, but they're also slower. And I'll show you a video of the environment here. Yeah. Cool. So if we look at some learning curves, on the left is basically demonstrating that SESMA is more sample efficient than MADDPG and independent DDPG. Independent DDPG is just the DDPG equivalent of independent Q-learning. So this first red curve here will be the number of episodes that the centralized expert takes, and then this second red curve will be the number of episodes that the decentralization part takes. This this dotted line is basically just an extrapolation of the reward, because we stopped decentralization early when the reward is of the decentralized agents sufficiently reaches the centralized experts level of reward. And as you can see, SESMA is more sample efficient because it achieves a higher reward in less episodes than MADDPG and independent DDPG. On the right, we demonstrate that SESMA is able to achieve a better optimum. It's able to find better agents. So here, we basically train MADDPG, independent DDPG, and SESMA and the centralized expert so that the reward curves plateau. And so as you can see, MADDPG plateaus here, and independent DDPG plateaus here, but the centralized expert plateaus much higher. It's able to achieve a higher reward, and we're able to decentralize this, seen in the red curve. We're able to decentralize this centralized expert, and so we find a better optimum. Now I'll talk about the StarCraft 2 environment, which is a strategy game where players micromanage armies in order to defeat their opponent. If we take a look at the screenshot here, we see that these agents are non-homogeneous, and there are 8 of them. Now the blue units are us, and behind each unit will be an individual neural network controlling it, and they'll be trained by SESMA. The red units are computer AI that was programmed by the developers, and we set the difficulty setting to be the hardest difficulty setting. In here I'll show you a video of the environment running where the blue units are trained by SESMA. Now, if we look at the reward curves, we see that SESMA is able to, okay, so on the left is the win percentage, right? And we see that SESMA is able to achieve a very high win percentage. And we're able to also decentralize this. So it also achieves the same high win percentage, sometimes even reaching 100% win rates. But of course, independent Q-learning suffers and just sort of stays in this low win percentage regime, probably due to the non-stationarity, non-Markovian nature of independent Q-learning that independent Q-learning suffers from. All right, well, thanks everyone for coming to my talk. Please check out the paper, Decentralized Multi-Agents by Imitation of Centralized Controller. We have more things in there. I wasn't able to talk about everything because I didn't have enough time, but you know, I do talk about how communication can play into SESMA and how to do that stuff, and we also have more experiments. All right, thanks for listening, and have a good day.